Hi guys, this is Math 148 in section 9.3, and the other important topic, in addition to the average rate of change that we cover in this section, is the definition of a derivative. And it's very mathy and heady and a lot of language, but here's the gist of it. On the bottom of page 570, your author writes, the function that gives the instantaneous rate of change of a function is the derivative. So this is a little hard to understand. Just the language of it's a little muddled, but let me read that again. The function that gives the instantaneous rate of change of a function is called the derivative. So for me, the way I always thought of derivatives is you have some function that goes like this, whoa, ooh, whoa, like that. It's a fun function, it's a roller coaster. And the derivative is always looking at what is the slope of the tangent line at any one point. Okay, that wasn't very tangent, was it? There. Come on, paint. So it's like here it's going fast, and then when you get to the top, it levels out for a second. If you were on a roller coaster, you could feel this, and then you'd be like, oh, it speeds up, so now the slope is changing. Okay, this is going to be hard for me to draw the tangent. It's going to be tangent to the line, and on the bottom it slows down. So imagine at each point, if you just took one point, what is sort of how, either think of it as how fast you are traveling, or what is the slope at that point of a line that is tangent to the curve at that point. So I will look for more videos online that go into more of the theory of derivatives to help you understand it. But in this video, I wanted to show you the formal definition and how to work some problems using the definition. So, in general, the derivative is the function that gives the instantaneous rate of change. That's the derivative. But here's the formal definition. Page 571. The first derivative, f prime of x, is the limit, this big messy thing, as h goes to 0, of f of x plus h minus f of x minus h. Where does this come from? Well, I'm not going to explain the derivation of this derivative formula at this point. I would just like to show you how to use this formula. Although it's basically saying it's the limit as h gets small. You're again approaching that rate of change over the function. So if the first derivative exists, if this limit exists, then we say f is differentiable at c. So again, this is the limit formula, and I want to show you how to work a few problems that are using this formal limit definition. So the first problem that I will go over with you is question number 15. Hello, pen, come to life. Question number 15 in this section, and we have f of x, come on, baby, f of x equals 5x squared plus 6x minus 11. And the question asks you to find the derivative using the definition of the derivative. Section 9.3, rates of change. Sorry, I was flipping through the book trying to make sure I'm reading exactly. Yes. Find the derivative by using the definition. So using the definition, this is what they mean. Definition. Okay. This is what that's saying. So we want to find, here's the definition right here, right? That thing. So the first step, and this is sort of nice, your book gives you a procedural box. Procedural box on page, what is the page? The procedural box page is 571. So if you want to follow along these steps, you can look at page 571. So the first thing you want to do is find f of x plus h minus f of x. This is step number 1. We're finding the derivative using the definition. Okay? So it's a little tricky, but sort of you just have your system and you crank through it. So the first thing we do is we plug x plus h into here. 5, when I say here I mean all of this. 5x plus h squared plus 6 x plus h. This is the function evaluated at the point x plus h. You'll notice there's no x plus h, no x function here, that's just 11. Minus and then minus f of x. Well, that part's easier because f of x is just what we're given, x squared plus 6x minus 11. This is the formal way to find the derivative using the definition. So now I expand this out. This is 5x squared, this part here, x plus h squared. X squared plus 2xh plus h squared, like that, 5 times all of that, plus 6x plus 6h minus 11 minus, now we have to be careful with our minuses, 5x squared minus 6x plus 11. What happened? A minus is a plus. Okay, now we have to write this out again. So I'm just expanding. Some of you may write all of these steps. Some of you may condense your steps a little bit. 5 times 2 is 10. xh plus 5h squared. And then we have plus 6x plus 6h. Okay, minus 11 minus 5x squared minus 6x plus 11. Breathe. And now we get to cancel. I love to cancel. Love it. Minus 5x plus 5x. Okay, what else we got? What else? I'm searching. I got a 6x. I got a minus 6x. I got a plus 11. I got a minus 11. Oh, I love it, you guys. Love that. So this whole thing now is reduced to 5h squared plus 10xh plus 6h. Why are we doing this? What have we done? Again, we're looking, the big goal here is to find the derivative, the first derivative, using the definition. So first we found x plus h minus f of x. So the next step, we have step number 2. Step number 2, we want to find f of x plus h minus f of x, divide this whole thing by, divided by h. Why would we do that? Well, again, if we look at this definition, we're finding this part, f of x plus h minus f of x divided by h. We're kind of closing in on it. So we're going to take this whole thing and divide it by h. Guess what? We get to cancel. I love to cancel. The h squared, that leaves an h there. xh, that just cancels, leaving the x. So this whole thing reduces to 5h plus 10x plus 6. 5h plus 10x plus 6. Let me get a new picture. I need more space. One of my frustrations with Paint is that it doesn't just scroll up. But that's okay. So again, we said f of x plus h minus f of x all divided by h. This is equal to, I just said it was 5h plus 10x plus 6 from the previous work. You can rewind it on your video. So if you want the limit of this, as h goes to 0, this is step number 4 in your procedural box. We just take the limit now as h goes to 0. So as h goes to 0, this piece goes to 0. There's no h here, and there's no h here. So this whole thing just equals 10x plus 6. 10x plus 6. Hold on. Number 15, and part A said, given the function, find the derivative by using the definition. Haha, we did that. So this is f prime of x, like that. That's where you say a derivative right there, f prime of x. Part B of the question says, find the instantaneous rate of change at any value and then at the given value. So we want the instantaneous rate of change. Oh my word, you guys, there's people walking in front of our house. Can you hear that party? Oh, my dogs are gonna freak out. Okay, hold on, gotta wait for the people. Okay, so the instantaneous rate of change at any point, they're just being tricky now. They're just kind of helping you get used to these definitions. That is equal to the first derivative. So that is the same thing as f prime of x. So in this case, we can say, haha, at any point, we already found that. It's 10x plus 6. And then if we want to do it at the given point, they give us a point, that is x equal to -2. All right, we can do that. So we're just going to plug -2 into this function. So the instantaneous rate of change at -2 is the derivative evaluated at -2. So that's -10 or +10 times -2 times +6. That's -20 plus 6 is equal to -14. So that is the instantaneous rate of change at the point x equals -2. So these problems take up some paper. You guys are going to want to get some extra little scratch paper sitting around so you can do these long derivatives and using the definition. So part C says find the slope of the tangent line at the given point. The slope of the tangent line. Again, they are just using these different parts to help you understand the different definitions of a derivative. The slope of the tangent line to the function at the point x equals -2, well, that is the same thing as the derivative evaluated at -2. And we just did that. So that's equal to -14. And this is what it's saying. So here's our function. I believe I graphed it here. Here is the function x squared plus 6x minus 11. So it's a parabola. We can zoom in on it if you like. And there's some point here, -2. Where is it? -2, where does it hit it? Right there? No, a little more, a little less. There, -2. So imagine if I draw a line that is tangent to that point. It's going to be hard for me to draw because this is pretty steep, so it would look the same. But what is the slope of that line? Well, the slope of that line is -14. So I just want to point out, this is not the equation of the line. This is the equation that gives you the slope of the tangent line. It's just giving you a bunch of different slopes of the tangent line. Finding the equation of that line that is tangent involves a little bit more work. And I want to do one more thing. I don't want to get involved in finding the equation of the tangent line right now. I just want to make one last comment about derivatives. So the first derivative, is sometimes called f prime of x, but it's also sometimes called dx, where all my choices, dy, sometimes we say dy, dx, sometimes we say it's the derivative dx, ddx of f of x. There's all these different notations that we use. Sometimes we use this. We say d, the derivative evaluated at x of y, and sometimes we say the derivative evaluated at x of f of x. There's so many notations, and it's also, the derivative is the instantaneous rate of change, and it's also the slope of the line that is tangent to your curve at a given point, at any point or at some point. And we're going to be doing a lot of derivatives, ways to calculate derivatives and interpretation. So I don't expect you to get all of these interpretations and have it make sense right away. But I just wanted to introduce you to these different notations. And it's also equal to, here's our formal definition, the limit as h goes to 0 of f of x plus h, my plus got involved in my x, minus f of x all divided by h as h goes to 0. So I want you to be able to do a few of these derivatives, be able to do them using this definition, and then in the later sections we'll do more applications of derivatives and a lot of formulas that will speed things along so that you're not doing this all the time because it gets a little flat-lined, a little slow. Okay, that's that.